Welcome to a deep dive into quantum computing. Looks like you've been doing your homework.
Yeah, there are a lot of great resources out there.
You've sent in articles, research papers, even some handwritten notes.
Yeah.
You're serious about this, huh?
Definitely. It's a fascinating field.
And we're here to help you sort through it all.
Right.
So quantum computing, it's kind of like regular computing, but, well, quantum.
Yeah, it's a whole different way of thinking about computation.
We've got these quantum algorithms.
Right.
I mean, we all know how regular computers use algorithms, right? Step-by-step instructions.
Exactly.
But quantum algorithms, they're not just faster, are they?
Well, in some cases, they are exponentially faster.
But it's more than just speed, right? It's like they're doing something completely different.
They are. They leverage these strange quantum phenomena, like superposition and entanglement.
Okay, stop right there. Superposition. Entanglement.
Right.
Those are words I've seen in your materials.
Mm.
But to be honest, they still sound a bit like, science fiction to me.
Well, they are pretty mind-bending concepts.
Can we break them down a bit? Like, starting with superposition.
Sure. So in a regular computer, you've got bits, right? They can be either 0 or 1.
Right. The foundation of everything digital.
Exactly. But a quantum bit, a qubit, it can be in a superposition. It's both 0 and 1 at the same time.
Both at the same time. How is that even possible?
It's kind of like, imagine a spinning coin. Before it lands, it's got the potential to be heads or tails.
Okay, I can kind of see that. So it's not decided yet.
Right. It's in this fuzzy in-between state, and that's what gives quantum computers their power.
So they're exploring all possible solutions at once.
In a way, yes.
Okay, that's superposition. But what about entanglement? That's the one that really gets me.
Yeah, entanglement is even weirder.
Because now you're talking about, like, two of these spinning coins, right? And they're somehow linked.
Exactly. Imagine, no matter how far apart those coins are, if one lands on heads, the other one instantly becomes tails.
Whoa. Okay, that's just messed up.
It is, right? It defies our classical intuition about how information can travel. But that's how qubits can be linked.
And that's what makes quantum algorithms so powerful.
Part of it, yeah.
So can you give me an example, like a specific algorithm that uses this stuff?
Sure. There's Shor's algorithm. It's actually the one that's got a lot of people worried.
Worried? Why worried?
Well, Shor's algorithm can factor large numbers.
Okay. And why is factoring large numbers a big deal?
It's the basis of a lot of our encryption, like the stuff that keeps your online banking secure. It's incredibly hard for a regular computer to factor a large number. It would take years, maybe even centuries.
But a quantum computer, using Shor's algorithm,
could crack it in a fraction of the time.
That's kind of scary.
It is. It's a real threat to cybersecurity. That's why there's a lot of research into post-quantum cryptography.
New ways to encrypt things that even quantum computers can't crack.
Exactly.
Okay, so that's Shor's algorithm. Exponential speed up. Potentially world-changing.
Yeah.
But you've also mentioned other algorithms that offer, like, more modest speedups.
Right. Not every quantum algorithm is going to be like Shor's.
Okay, so like what? Give me an example.
Well, there's Grover's algorithm. It's good for searching. It provides a quadratic speedup.
Quadratic, so not exponentially faster?
Right. It's more like it can do a task in the square root of the time it would take a classical computer.
So if it takes a regular computer 100 seconds, a quantum computer using Grover's algorithm could do it in
10 seconds.
Okay, it's still pretty impressive. But what kind of practical problems could this actually solve?
Well, imagine you're searching through a massive database.
Like Google.
Sure. Or even bigger. Like searching through all the genetic data we have.
Trying to find a specific gene sequence.
Right. A classical computer would have to look at each entry one by one. But Grover's algorithm could narrow down the possibilities much faster.
Okay, so instead of searching through millions of entries, it's like it can pinpoint the right one much quicker.
Exactly. It's like having a super efficient search engine.
Okay, but we're still talking about algorithms, calculations, stuff on paper. What about real-world applications? Like things that would actually impact our lives?
Well, that's where things get really interesting. One of the most promising areas is in scientific simulations, simulating how atoms and molecules behave.
Ah, so like chemistry stuff.
Yeah.
But why is that so hard for regular computers?
Because we're trying to simulate a quantum world using a classical computer. It's just not very efficient.
It's like trying to fit a square peg in a round hole.
Exactly. But a quantum computer, well, it speaks the same language as the systems we're trying to simulate.
So it's a much more natural fit.
Exactly.
But what kind of breakthroughs could we actually see from these simulations?
Well, you seem particularly interested in quantum chemistry based on the material you sent in.
I am. I mean, it just seems like there's so much potential there.
There is.
Can we dive into that a bit more?
Sure. Imagine designing new materials with specific properties, like superconductors, that work at room temperature.
Wow, no more needing crazy expensive cooling systems. That would be huge.
Right. Or catalysts that can make chemical reactions way more efficient. And greener, too. Less waste, less energy consumption.
We're talking about transforming entire industries here. Energy, transportation, manufacturing. The possibilities are kind of mind-blowing.
They are. And drug discovery. Imagine designing drugs that target specific diseases at the molecular level, like zeroing in on the problem with pinpoint accuracy.
Personalized medicine, tailored to your unique DNA. That's the holy grail, isn't it? But how far off is all this? Are we talking decades before we see real-world applications?
Well, quantum computing is still in its early stages. Building and controlling these machines, it's incredibly challenging. But the progress is remarkable. One of the articles you sent in talked about how IBM used a quantum computer to outperform a classical supercomputer on a specific physics problem.
So they're actually starting to deliver on some of these promises. It's not all just hype.
Exactly. It's a proof of concept that quantum computers can tackle problems that are just impossible for classical computers, even the most powerful supercomputers we have today.
Okay, so back to cryptography for a second. We talked about Shor's algorithm and how it could crack current encryption methods, and the need for post-quantum cryptography. Can we dig into that a bit more? Like, what are the options?
Sure. So remember, Shor's algorithm can factor large numbers, exponentially faster than any classical algorithm. And a lot of our encryption methods rely on that difficulty. RSA, Diffie-Hellman, these are the workhorses of cybersecurity.
The stuff that keeps our online transactions safe, our emails private.
Exactly. But with a powerful enough quantum computer, those systems would be vulnerable.
So what can we do about it? Is it a losing battle?
Not necessarily. There's a lot of research happening in post-quantum cryptography, new ways to encrypt information that are resistant to quantum attacks.
Like what? What are some of the approaches?
Well, one promising area is quantum key distribution, QKD.
Yeah, I've seen that mentioned in some of the articles. It's like using the properties of light to transmit keys.
Right. It leverages the principles of quantum mechanics to ensure secure communication.
So instead of relying on mathematical complexity, it's using the laws of physics to make it unbreakable.
Essentially, yeah. It's about encoding information into the quantum state of photons, those tiny particles of light.
And because of these quantum properties, any attempt to eavesdrop would be detectable.
Exactly. Any attempt to intercept or measure those photons would inevitably alter their state, alerting both the sender and receiver.
It's like a self-destructing message. If anyone tries to read it, it disappears. Pretty cool. But is it practical? Can we actually build secure networks using this technology?
It's already happening. QKD is being used in some niche applications, like securing financial transactions and government communications.
So for high-stakes stuff, it's already here. But it's not going to replace our everyday encryption anytime soon, right?
Probably not. There are still challenges, like the distance over which we can transmit these quantum keys.
So scaling it up to a global level is still a ways off.
Right.
But what I find really fascinating about QKD is that it's not just about securing existing communication. It's about building entirely new types of networks.
Quantum communication networks, you're right. It's about connecting different quantum computers, allowing them to share information and work together.
Quantum internet. We're talking about a whole new level of interconnectedness.
Exactly.
Okay, let's take a step back for a minute. Because while all this sounds amazing, there are still huge challenges in building practical quantum computers.
Right. Absolutely. It's not just about scaling up the number of qubits.
Making bigger machines.
Right. It's about maintaining their delicate quantum states.
Right.
Protecting them from interference. It's incredibly difficult.
So it's about quality, not just quantity.
Right. One of the major challenges is decoherence.
Decoherence, what's that?
It's when qubits lose their quantum properties due to interactions with their environment.
So like the outside world is messing things up.
Essentially, yeah. It's like trying to balance a spinning coin on its edge in a windstorm.
Okay, yeah, that's not going to last long.
Right. So researchers are working on ways to build more robust qubits, using different approaches, like superconducting circuits, trapped ions, even topological materials.
So there's not one clear winner yet. It's like the Wild West of computing.
In a way, yeah. It's a very dynamic field, a lot of different approaches being explored, and it's not just about the hardware. We also need new algorithms, specifically designed for these quantum computers.
So the software has to catch up with the hardware.
Exactly.
Okay, so we've got these incredible challenges, but let's shift gears for a moment and talk about the potential impact. We've talked about cryptography, simulations, but there are other areas where quantum computing could make a difference.
Absolutely.
What are some of the most exciting ones you're seeing?
Well, one area you seem pretty interested in is medicine.
Yeah, I mean, who isn't fascinated by the potential of quantum computing to like revolutionize healthcare?
Right. There's a lot of buzz about it.
For good reason, I think.
Yeah.
I've got all these articles here about how it could transform drug discovery.
Yeah, that's a big one.
Imagine designing drugs with, like, pinpoint accuracy, targeting specific diseases at the molecular level.
That's the dream, right? Personalized medicine, tailored to your unique genetic makeup.
No more one-size-fits-all treatments.
Mhm.
Minimize side effects, maximize effectiveness. It's incredible.
It is. And not just drug discovery, quantum simulations could also help us understand complex biological processes.
Yeah, I'm seeing a lot about that here, like protein folding.
Right, that's a big one.
Misfolded proteins are implicated in so many diseases. Alzheimer's, Parkinson's.
It's a really challenging problem, understanding how proteins fold.
But if we could crack that code,
It could lead to breakthroughs in treating those diseases.
it's like having a virtual laboratory where we can study these processes in incredible detail.
Exactly.
But it's not just about developing new drugs, is it? There's also the potential for faster and more accurate diagnosis.
Absolutely. Quantum algorithms could analyze medical images, like way better than we can today.
Helping doctors detect diseases earlier, when treatment is most effective.
Right.
That could be life-saving. It really seems like quantum computing has the potential to transform healthcare in some pretty profound ways.
I think so.
But what about other fields? I'm also seeing some interesting stuff here about artificial intelligence.
Yes, quantum AI. That's another area where things could get really interesting.
Because quantum computers could process information so much faster.
Right. Quantum machine learning algorithms, they could analyze massive data sets, find patterns we might never see otherwise.
So we're talking about AI that can learn faster, adapt more quickly, maybe even be more creative.
It's possible. We're still in the early stages of exploring all this.
It's exciting, but also a little bit unnerving, right? Like, what happens when we create AI that's potentially smarter than us?
That's a valid concern. As we develop these powerful AI systems, we need to think carefully about the ethical implications.
Make sure they're aligned with human values, that they're used for good.
Absolutely. It's a conversation we can't afford to ignore.
But on a more optimistic note, what about the potential of quantum computing to address some of the world's biggest challenges, like climate change?
Yeah, that's another area where quantum computing could make a real difference.
I'm seeing some articles here about how it could help us design more efficient solar panels, develop new catalysts for carbon capture.
Right. Or even discover entirely new materials for energy storage.
So we're not just talking about incremental improvements, we're talking about game-changing breakthroughs that could really help us transition to a more sustainable future.
That's the hope.
It's pretty amazing to think about all the possibilities.
It is. But it's important to remember that quantum computing isn't a magic bullet.
Right. It's not going to solve all our problems overnight.
It's a tool, a very powerful tool, but it needs to be used responsibly, ethically.
If we do that, then yeah, it could help us address some of the most challenging problems facing humanity.
I agree.
Well, I think this has been a really fascinating deep dive. We've covered a lot of ground, from the fundamental principles of quantum mechanics to the potential applications that could really change the world. But as we wrap up here, it's worth reiterating that we're still in the early stages of this quantum revolution.
We are. There are still many challenges ahead, both technical and ethical, but the progress is remarkable. And the possibilities, well, they're pretty mind-blowing.
So the key takeaway for our listener is this. Quantum computing is not just science fiction. It's a rapidly evolving field with the potential to transform our world in profound ways. And it's a journey that we're all on together. So stay curious, keep learning, and let's see where this incredible technology takes us. Thanks for joining us on this deep dive.